I've talked about how we have this equation which says that the total momentum before two balls collide is the same, must be equal to the total momentum after they bounced off. Now this equation looks like it has just come out of nowhere. It's not obvious why it's like this, and it looks complicated. Now I'm going to give some idea about where it comes from. Actually, it comes from Newton's laws directly, and actually prove that that's the case, and we can derive it. But I'm just going to give a rough idea, okay, about the connection, so that you can see that it's just it did not just appear out of nowhere. Okay, the first step is this. Let me rearrange this equation a little bit. Let's see, how shall I do it? I have this part here. Let me just remind ourselves about where the numbers come from. So M1 U1 comes from here, comes from this ball, the momentum of the yellow ball. Okay. M2 U2 comes from the momentum of the green ball, and M1 V1 is the momentum of the yellow ball after colliding. Okay, and this one is from the green ball after colliding. Now what I'm going to do is this. I am going to group momenta for the same ball. For the yellow ball before and after colliding, I'm going to group those two together, and I'm going to group the momenta for the green ball together, meaning that I'm going to rearrange them. Okay, here's what I'm going to do. Okay, I'm going to do this, right? U1, M1, and I'm just going to write this out first. M1, M2, M2. Right, and I need an equal sign there. So I'm going to rearrange this. I would keep the U1 here. Alright, so M1 U1, oops, the same. I'm going to move the M1 V1 over to the left. So I get a minus M1 V1. So in this way, I've moved the yellow ball, momentum for the yellow ball, alright, which has mass of M1. Move its momentum to one side, to the left side. And now let me look at the green ball. So for the green ball, let's see, the mass is M2. Okay, starting velocity is U2. Final velocity is V2. So I'm going to keep the V2 here. Same as that. Change. I'm going to move the M2U2, the momentum before colliding, to the right. So M2U2. Okay, and there's a minus sign here, since I move it to the right. Okay, before that, let me use the same color scheme. I've used white color for V1, so I'll continue to use white color here, so that it's easy to follow. Use white color for the after collision velocities, and the before collision velocity I've used green color. So I'm going to continue to use green color for U. green color is before collision. Oh, alright. And I have a plus sign there. Okay, I have a plus sign there. So this is what I've done. I have moved all the momentum for one ball to for each ball to one side. So that's the yellow ball. That's the yellow ball. Okay, if it's easier, I'll use a yellow line to underline this. This is for the yellow ball, momentum for the yellow ball, and for the green ball, these are the momentum. Now, why am I doing this? If you look at this, say the left side for the yellow ball, I have the difference between the final momentum of the yellow ball, meaning after colliding, and the initial momentum before colliding. So, in other words, I have the change in momentum of the yellow ball on the left side. And on the right side, see, that's this minus m2u2 is the initial momentum of the green ball before colliding, and m2v2 is the final momentum of the green ball after colliding. So on the right side, actually, I have the change in momentum of the green ball. So what I've done is I have now after rearranging, I actually have found some meaning, some physical meaning I can use to describe each side of the equation. So let me write down this observation. Okay. So on the left side, right, on the left hand side, we have actually the change in momentum of, I'll call it of ball 1. Okay, ball 1 is this one, is my yellow ball. Okay, that's ball 1. And on the right side, I have the change in momentum of ball number 2, the green ball. So change in momentum of ball 1. Okay, and on the right side, I have the change. I'm running out of space here. The change in momentum. I'm just going to use MOM, short for momentum, of ball 2. And that's my equation. I have this equation here. Okay. Now, I'm going to be a little bit more precise at this stage, so that we don't get confused afterwards. Now, coming back to this change in momentum of ball 1, notice that I have here the initial momentum m1u1 minus the final momentum m1v1. But remember that when we talk about change, we should always take the final value minus the initial value, and not the initial minus the final. So if I take the initial minus the final, what I really have is a negative of the change. Right? I'll get the negative value of the change. So, but the magnitudes are the same, right, of the two changes. So this is what we got this from this momentum conservation equation. So let's try and understand why the change in momentum of each ball has to be the same. So coming back to this picture where the two balls were in contact. So when they were in contact, right? Remember that there's this force from the yellow ball pushing on the green ball, and at the same time there is the equal and opposite force from the green ball pushing on the yellow ball. And it is this pushing force that causes the change in momentum. And we understand that from Newton's second law. Okay, now force and momentum. Okay, let's see. I have the green ball pushes with a certain force, and the yellow ball pushes with a certain force. And they are equal and opposite. They are equal and opposite. Okay, so what we want to do now is to find out the connection between the force and the change in momentum, and that's something that that we can use. That's something that we can use Newton's second law to tell us. Newton's second law, if you remember, says that force is equal to the change in momentum divided by the time. So the change in momentum, so that will be m1 mass times velocity, mass times, say, the final velocity, minus the mass times the initial velocity. Okay, so final minus initial momentum divided by the time taken. So in this case, we have a force, right? We have a force, and the ball, when the ball hit each other, they get squashed a little bit. Okay, while they're in contact, they get squashed a little bit, and then they bounce off again. So the time here would be the time during which the balls were in contact, right, in the process of being squashed and then rebounding. So that's the time here. Now what we can see here is that the force, right, the important point about Newton's equation here is that the force is directly related to the momentum over the change. Okay. Now let me rewrite this to make the change in momentum part more explicit. So mv minus mu. I'll multiply both sides by t, so that t comes over to the left. So F times T is equal to this change in momentum. Now think about this equation for each ball. So let's say the yellow ball exerts the force on the green ball. Okay, exerts a force on the green ball. So that force is F, and it pushes against the green ball for a time T. Now, of course, during this time T, the force may not just stay fixed, it may increase and decrease in a complicated way. But for now, I'm not going to worry about that. I'll just take it that maybe the force is fixed. So a force times time. The time is also is, let's say, t. Okay, that this force times time from Newton's second law. We know that it is actually equal to the change in momentum. Okay, so that's that much we understand. Okay, from the about the force from the yellow ball pushing on the green ball. Okay, so this force acting over this time t causes this change in momentum in the green ball. Now let's turn round and look at the yellow ball. Okay, look at the yellow ball. Now I'm going to make this. Now for the yellow ball, okay, I have the force from. Now let me before that, let me clarify this thing a bit. This force comes from the yellow ball. Okay, and this change in momentum is the change for the green ball. So it's more tractable. The time is common for both balls. So, but never mind. Let me just say that this comes from the yellow ball. Now, from the green ball, I have a force that acts on the yellow ball. So let me write that down. So the force from the green ball pushes on the yellow ball for a time t. So same force, same time actually, same magnitude of force at the same time. And this must, according to Newton's law, second law again, cause a change in momentum of the yellow ball. So I'll write that down, exactly the same formula, mv minus mu. Same formula, but for the yellow ball. Okay, so F and T, force and time, acting on both balls, have exactly the same magnitude. But the balls, of course, have different masses and velocities. So since this is for ball 1, I'm going to use a subscript 1 for this. Alright, just like I've used for this momentum equation. And for the green ball, okay, I'm going to label them by 2, the subscript 2 for all the masses and velocities. Now if you look at those two equations, okay, the masses and velocities are different, but the forces and times have the same magnitude. So clearly, because the forces and the times are the same on each ball, right, they will cause the same change in momentum for both balls. So there we have our explanation. We have our explanation about why this change in momentum of ball 1 is equal to the change in momentum of ball 2. Okay, so let me just tie up one loose end. There's this minus sign there, alright, that I've not explained. And the reason for that comes from here. It comes from the fact that the two forces here are actually equal and opposite. Okay, and if I'm going to choose the right side as positive, then what I can do is I can, if I let's say if I think of the force from the green ball as F, then when I put in the direction, okay, the force from the green ball is pushing to the left, so I should have a minus sign there to show its direction. The force from the yellow ball, a plus sign, since it's pushing to the right. So therefore, just to make it more correct, I should have a plus sign here for the yellow force from the yellow ball, and a minus sign here for the force from the green ball. Okay, so that's how the signs comes about, right? This tells us that this momentum change of the yellow ball must have opposite sign to the momentum change of the green ball. So that's why when we have this equation here which says that the change in momentum of the two balls are equal, we have an additional sign to tell us that they are equal, that the changes in momentum are equal, but they are in the opposite directions.